the results from phase 1 of the project on electromigration of tin Bismuth and SEC 305 solder for the second level interconnect project. Okay. We had a webinar 2 weeks ago. It's talking about the results based on the planar test vehicle. Today, we will talk about the results that we used on bottom terminated component test vehicle. So this project is chaired by Dr. PJ Sun from IBM. The co-chair is Real Espedia. He's from Intel Foundry. Myself, I'm Hailey Fu. I'm facilitating this project from the NEMI staff end. Okay. Today's webinar will include the phase 1 report, as said, the second portion of the results, and also we will introduce a little bit what we are going to do for phase 2. Okay. Next. Next slide, PJ.
Okay.
So the outline of today's agenda, we will give an overview of the whole project and the timeline, then focus on the results on the second portion, as mentioned on the bottom terminated component test vehicle, then introduce phase 2 and how to sign up to join the second phase if you are interested. The presentation material and recording will be shared. So at the end of this presentation, we will open the floor for questions and answers. You can use the chat or Q&A to input any of your comments. We will go through that, okay, during the Q&A. So as you can see, this is the overall project schedule. We started some discussion about the electromigration potential risk, especially on the Bismuth tin solder joints. When the current density goes up, and there is a potential the Bismuth may saturate at the anode end. So then there may be some mechanical reliability risks increase. So we started to form the project team and define the project details. Basically, this is done in 2021. And we started the test vehicle development and established the project plan with the test vehicle and get the resource ready. Explore in phase 2, explore the effect of the current density, the temperature, solder joint height, surface finish, the effect of some minor alloy additions. So this work is almost accomplished. So today's webinar will only introduce the results here. For the phase 2, we will study the how the impact of electromigration may impose on the mechanical shock, those reliability. So, as you know, the Bismuth tin solder joints could be brittle, so the mechanical shock is a concern. And also there are some factors that we would like to deep dive from the phase 1 study, some learning there. We want to understand if there is a back pressure impact that's a potential mitigate the electromigration. Also, we will study the underfill on the electromigration rate in the solder joint. Okay, and then the future phase would be consider the use conditions for the electromigration. So currently we are at the end of phase 1 and starting the second phase. Okay, next slide. So here are the list of the participating members from the phase 1. So we have several of the OEMs or IDM companies, and also material suppliers participating in this project. Next slide. So I will hand over to PJ. As mentioned, we have 2 test vehicles. So PJ will go ahead and introduce the work that we did on the electromigration. So PJ, go ahead.
Thanks, Haley. So in this project, we have taken 2 approaches to study electromigration. One is just a standard bottom terminated component, like a BGA solder joint. The other one is our invention, which is the planar solder joint. So in the case of, so this presentation will be in BGA, but let me just say a few words about planar geometry test vehicle. In this case, we have a planar solder joint, which is highly polished. So not only can we observe the electromigration by observing the change in resistance of solder joint, but also we can observe the microstructural changes. So this is a very powerful technique, and we presented this the results from this approach last week. But today we will talk about testing BGAs, bottom terminated component solder joints. So that's today's presentation. And so that's study of, so I have 2 parts to it. Study of tin bismuth electromigration and bottom terminated component solder joints. Also study of SAC solder. So we're studying both the tin bismuth and SAC solder in this presentation. So to repeat myself, we will determine the electromigration rates in eutectic tin bismuth bottom terminated component solder joints, and we will study 2 finishes, organic solderability preservative and gold on electrolyzed nickel. So we'll see the effect of these finishes on electromigration. Ultimately, the objective is to predict the electromigration life of a solder joint under any current density or temperature conditions. So here is the test setup. So these cards were built by Intel. Here you see the daughter card without the component, and on this right side you see the component soldered to the daughter card, and it's the solder joints between the component and the circuit board that we are studying. So what we do is we have 4 solder joints, but only B and C are the ones we pump current through. So current flows like this. There is no current in A or D. So A measures the voltage drop across B, and D solder joint helps to measure voltage drop across solder joint C. And since we know the current, and if you know the voltage, we can measure the resistance of solder joint B and C. And here is just a cross-sectional view of the 4 solder joints. And I won't go into any details, but what we do is we measure the joule heating for many, many specimens, and we measure the power dissipation. So we get essentially a straight line that goes through almost 0, which it should. And from then on, since we know the power dissipated in a solder joint, we can calculate the joule heating temperature, and we add that to the oven temperature to get the true temperature of the solder joint. So here is an example of a cross-section of a tin bismuth solder joint. So current is flowing, electrons are flowing down. This region here is bismuth-rich phase, mostly bismuth. And on the top here is gray region, which is tin phase, tin rich phase. In between, we call it near eutectic. So basically, the bismuth atoms are moving down and collecting at the anode. And as this bismuth gets thicker, the resistance increases, and we use the resistance as a measure of electromigration. Now here, there's a K missing, 3 kiloamps per centimeter squared. Okay, so what we learned in our study is when you plot resistance versus time for a solder joint like shown here, initially there's a dip in resistance. Then the resistance rises. It kind of becomes linear for some period, and then it becomes parabolic. So let me explain why we have these three regions. So, okay, before I do that, this is an actual data. This was just a cartoon, but here, this is actual data for different solder joints. So we have the dip region, we have the linear region, and then we have the parabolic region. So the reason we have the dip is because initially the structure is very fine. So the white region is bismuth, the gray region is tin rich. So imagine electron flowing through this region. It wants to go along the dark region because that's tin, is more conductive, but it meets many obstacles. So it meanders through to get from the cathode to the anode, whereas after a few days, the structure becomes very coarse. And now you can see it's easier for the electrons to go through the gray region, so the resistance decreases. So that's the reason for the decrease in resistance, this small decrease. And then the increase happens because the bismuth starts collecting at the cathode, at the anode, and become thicker and thicker. That gives us a linear region. And then we get to the stage when the bismuth gets very thick on the anode, but there's not enough bismuth left to feed this region. So then the thickness cannot increase. So thickness increase becomes slow. That's when the resistance kind of plateaus. We get the parabolic region. So that explains the shape of the curve. Now, to study electromigration, we take the linear region because this has all kinds of slopes, and this region, the dip region, has slopes. So we rely on this linear region to give us the rate of change of resistance, which we say is proportional to electromigration. So here is a calculation I won't go through, but the important thing to note is that dx over dt, in other words, So the solder joint is between copper on the top, copper on the bottom, and the bismuth from the eutectic collects at the cathode. So this x is the thickness of the bismuth, and dx over dt, the rate of change of this bismuth thickness, is proportional to current density J. And dr over dt is also proportional to J, but the important equation is that dr over dt, the rate of change of resistance, is proportional to the rate of thickness increase, and this is essentially constant. So keep in mind that we can assume that the rate of change of resistance is proportional to the rate of increase of the thickness of the bismuth. So I won't go through the page either, but in this equation, the drift velocity, the velocity of the bismuth atoms is equal to dF over kT. D is the diffusion coefficient, F is the force on the atom, kT, K is Boltzmann's constant, T is absolute temperature. So we can derive this equation that says drift velocity times temperature divided by the current density is equal to some constant e to the minus kt. And so we say that the drift velocity is proportional dx over dt, which is proportional dr over dt. So we replace v by dr over dt, and we put a constant c1. Then we take log on the two sides, we get this equation. So I'll show you plots of log of rate of change of resistance times temperature divided by current density is equal to minus q over k times 1 over t. I think there's a constant here which is missing, but we don't need that now. So essentially, we plot the log term versus 1 over t, and but getting back to what rate of change of resistance do we use? So we stay with the linear region. And then this is an actual data. So this is 100 degrees centigrade, 4.5 ampere current. And you can see the curve is parabolic and there is no dip. The reason there's no dip is current is too high, so the dip is very short. So we just take the slope of these curves as a measure of electromigration. And so previously it was 100 degrees, now it's 60 degrees at 2 amps. So low temperature, low current. And now the dip lasts a long time. So we have to wait for a very long time to get the linear region at low temperatures and low currents. Anyway, so here are the results. So we have three finishes: OSP, which is blue data points, ENIG, which are red, and ENIG OSP, which are green. And you can see they essentially fall all on the same plot. And the activation energy is 0.6 to 0.66. Activation energy is the slope of the line. So all these three lines are very similar slope. So conclusion is that the surface finish doesn't play a critical role in electromigration. So this chart basically shows how to predict the life of a solder joint. In this case, we are saying is 11 years. When the temperature of the solder is 60 degrees, here's the cross section of the solder joint. We're saying 1 amp current and 0.5 milliohms increase in resistance is the failure criteria. So this is simple math, and we conclude under these conditions, the life is 11 years. Now, this first term, log of dr over dt times temperature divided by J, this we obtain from this plot. That's so given the temperature, we know 1 over T, and then we can find this term. Once we know that term, we know what temperature is, we know what current density is, so we get dr over dt is 1.27 times 10 to the minus 4, and we say that a failure criteria is 0.5 dr, 0.5 milliohms, so we can find dt as 11 years. So that's straightforward. So conclusion of the first half of today's presentation is that tin bismuth eutectic solder exhibits three stages of electromigration behavior. And the eutectic solder, tin bismuth, whether it's between OSP metallization or ENIG or OSP, they exhibit very similar electromigration behavior with an activation energy of 0.6 to 2.66. And as I explained, the Arrhenius plot can be used to predict the life of the solder joints if we know the temperature and the current density. So this is the first half. So second half of today's presentation is similar presentation, but now we are studying SAC 305. So SAC 305 is 3% silver and 0.5% copper. So SAC 305 is very commonly used solder. So the objective here is to explain the shape of this curve. So we have resistance versus time. So for the longest time, the slope of the resistance increases very shallow, and then it shoots up. So why do we have this shape? And just as a repeat, SAC 305 is a tin-based solder containing 3% silver and 0.58% copper. And we're explaining why this happens. Everybody knows that this steep rise is because of voids. They grow the cathode, they coalesce into an open circuit. But what happens in the early stage? We'll explain that in this study. So again, I showed you this picture using the same setup, no change here. And okay, so what we do is we measure the resistance of the solder joint as a function of time. So we start off with the oven temperature at 125 degrees, and we measure the resistance, which is the black line. Then we drop the temperature to 110 degrees. That's the oven temperature, and the resistance drops, but it increases slightly. There's a jog, a slight increase. In the third portion of the test, we drop the temperature of the oven to 90 degrees, and the resistance drops a little bit. So now there's a jog in the resistance when we change temperature. That's because the temperature coefficient of resistivity. So when we drop the temperature, the resistance also drops. But we are using resistance as a measure of electromigration. So we need to get rid of the effector temperature. So we use this equation here on the top right. We say, okay, at temperature T1, resistance is R1. But what will the resistance be if in our mind's eye, we cooled the sample to 25 degrees C? So this would be the resistance at 25 degrees C. And alpha is not known, but we use an alpha that gives us a good fit. In other words, notice, by the way, this purple line and this black line is the same thing. But in this right plot, we expanded the scale. So notice there are no jogs in this because we chose a good value of alpha, which is 0.004. We got rid of the jogs. So now we have three temperatures, 1, 2, 3. So we take three slopes and we can use them to plot the Arrhenius plots. So again, I'd shown earlier that we plot the log of rate of change of resistance times temperature divided by current density is equal to minus Q over K times 1 over T. So we're plotting the log of that function versus 1 over T, and we get the Arrhenius plots. Notice for the blue, which is OSP, the red is INIG, and green is INIG OSP. We get very similar results. So finishes don't play a role in electromigration, and so we get similar results. Doesn't matter what the finish is. So let's talk about why the resistance increases. So I showed over here, see resistance increasing, the black curve. So why does that increase? The reason is SAC solder contains 0.5% copper. Of course, it contains silver too, but it's the copper that is migrating. And copper atoms are fast diffusers in tin, the interstitial, the fast diffusers, and they collect at the anode. So when the concentration of copper at the anode gets to 39.8%, it precipitates Cu6SN5 based on the phase diagram. So if you look at this is tin, this is copper. At 39%, there's the intermetallic Cu6SN5. So when the composition of this alloy reaches 39%, Cu6SN5 precipitates and it grows in this direction towards the cathode. And we'll see that. So here is, okay, this is an important chart. What this is saying, if the electrodes were inert, did not metallurgically interact with the solder, didn't form intermetallics, then if all the copper migrated to the anode, how thick would it be? It would be only 0.68 micrometers thick. So there is not much copper in the SAC solder to give you any effect of growth of Cu6SN5. Not enough Cu6SN5 grows if the top and the bottom terminals are inert. In other words, the terminations do not interact with the copper. So my point in this is there's not enough copper in the solder to give you any significant amount of Cu6SN5. So the copper has to come from somewhere. And before I go there, let me just show you what happens if we do just thermal aging. If you do thermal aging on OSP soldered with this alloy, you get Cu6SN5, you get Cu3SN. So this is an intermetallic. If you have ENIG, which is mostly nickel, you get Ni3SN4. You can see the thickness of Ni3SN4. And then third case is OSP on the top, ENIG on the bottom. On the top, we get Cu6SN plus Cu6SN5. And the bottom, you get Ni3SN4. So nothing surprising over here, right? So now let's do electromigration. Oh, before I go there, so the question would be, at what temperature did we do this thermal aging for how long? And the answer is, first 80 days, we were at 126 degrees C, next 60 days, 111, and the third 60 days at 91. So these samples saw all these different temperatures, right? So now what happens when you pass current? The plot on the left is just thermal aging. There is no current. The one on the right, electrons flow down this way. And notice the huge difference between the two. So what happened in this case is that the copper in the top metallization dissolved and electromigrated into the tin, and it formed this intermetallic which grew from the anode towards the cathode. And it almost completely consumed the solder. And also notice the voiding. So voiding is because more atoms are flowing away from the interface than into it. So less atoms are coming in, more are leaving, and that is what is causing the voiding. So we get Cu6SN5 consuming the solder, and of course voiding. So this is OSP. ENIG is a different story. Here, the nickel is a good diffusion barrier, but I'll show you we do have cracks in the nickel. Copper does get through. So all this copper Cu6SN5 you see, that's because of copper coming from the top copper termination, metallization. Because I'll show you this porosity in the nickel plating. Again, the conditions are as before, 80 days at 126 degrees C, 60 days at 111 degrees C, 60 days at 91 degrees C, but also 4 ampere current. So this is electromigration experiment. Now, what about ENIG OSP? Now, on the top is OSP, on the bottom is ENIG, and the current is flowing down. So you can see the copper metallization dissolved into the solder, and the solder is mostly Cu6SN5. And Cu6SN5 has somewhat higher resistivity compared to tin. That's why the resistance goes up. Now here's a composite. So let me explain this. The top row is 4 ampere current. So electrons flow like so up through the solder joint and down through the solder joint. So that's why the Cu6SN5 collects on this anode side. And here, the anode side is on the bottom. And we get voiding over here, we get voiding over there. And the next one is 6 ampere. Again, electrons flowing up and then down. And the last one is 8 amperes. Again, electrons flowing up and then down. So notice, if you look at these charts, they don't seem to make sense. There's not much electromigration here, Not much over there. Why do you have so much here and here and here? I don't know. So, but I think it has to do with the copper getting into the solder. More the copper into the solder, the thicker the intermetallic. And this one is enig. Here you can see a lot less Cu6SN5, but it's still plenty. And that's because it's less, that's because of nickel diffusion barrier. And you do see voiding here. You see voiding here. And the voiding is there, but we don't see it in the rest because the magnification is low. So let me show you a picture with uh, at high magnification. So this is, okay, here's copper, here's nickel phosphorus, and then Ni3SN4, the very thin layer. But you see cracks in the nickel phosphorus. So I think that's where the copper atom diffused through. So here is the magnified view. So you can clearly see the voids, and you can see porosity in the nickel phosphorus plating. And this is the Ni3SN4. And so the copper does, the fact we have copper Cu6SN5 here, that just proves that the copper got into the tin from the top because the copper is flowing down uh, into the solder. So notice voiding occurs between copper and the nickel. So voiding is here between copper and the nickel phosphorus plating. So porosity happens because less atoms are reaching the interface and more are leaving. So that's the fundamental reason. So I've shown this plot before, but let me summarize that the slope of the plot gives us activation energy of 0.6 to 0.7. We also know from published work that tin copper intermetallic growth activation is 0.6 to 0.9. So they're similar values, whereas copper electromigration activation energy is 0.3. So we are saying that the electromigration activation energy has to do with tin copper intermetallic growth. So that's the conclusion. So here's the conclusion. So in the early stage of electromigration, before the resistance goes sky high, copper atoms migrate towards the anode interface. There they react with tin, forming a thick layer of Cu6SN5. And this is what causes increase in resistance. So as the Cu6SN5 layer grows, starting at the anode and moving towards the cathode, that's the main contributor to increase in solder joint resistance in the early stage of electromigration. But then later on, at the later stage, the voids nucleation occurs, they grow, they coalesce into one big void that spreads across the solder, the span of the solder, and completely covers the interface, and that leads to electrical open. Okay, so that's my part of the presentation. So Haley, you want to take over?
I see. Thank you, PJ. I see Rail is on the call. So
Oh, good,
Rail,
good.
yeah, probably you can introduce your plan for the second phase.
Yes, the second phase plan, we have three phases to this project. The first two, 1A and 1B, are done, and PJ, I believe, presented his whatever experimental results. The 1C is in progress and is probably going to be finished soon in this quarter, where we have looked at solders with very minor tin bismuth solder with minor other elements added, and seeing what effect that has on the electromigration resistance for the alloys. Then we are going to study the mechanical shock reliability of the BTC solder joints after they have been subject to current stressing, which, as PJ showed, results in a bismuth migrating to the anode end. The concern, that's one of the major concerns of the tin bismuth solder users because that bismuth is brittle, and that will to begin with, the mechanical shock reliability of the joints is a little bit lower than SAC, for instance. But if you have the bismuth at one end of the joint, it could make it even worse. So that is the reason why we have 2A. 2B is the black investigating the role of the back pressure effect, also called black effect, where if the solder joint gets too thin, there is no the migration doesn't occur because electromigration because of the back pressure developed if there is any bismuth migration. And C, there have been a couple of papers recently in the literature which seem to indicate, at least at the first level, that the underfill, if underfill is there surrounding the joint, the electromigration decreases. So we are trying to confirm that with the BTC solder joint rather than a first level solder joint. And the third one is to develop an electromigration model using most of the empirical data collected by PJ in the first phase, and to validate this model with the industry use condition. A lot of the data published in the literature, as well as some of what we have looked at here, is at temperatures and current densities that are a little bit higher than what we get in an actual product in the field, particularly for consumer computers like desktops, laptops, and client computers. So that's what we are trying to figure out, if those particular temperature and current density conditions for the high power components, for instance, how much of electromigration we can get. And the project details, the schedule is shown down there with various milestones shown out there. And I think by the end of Q1 of next year, we should be done with the phase 3. Next slide. This is just a setup of the mechanical shock reliability assessment that I am talking about, where we use the BTC component. We mount it on a JEDEC test board, the B11A design, which is is used in the industry for a lot of shock testing on components that are used in mobile products. And then these boards are plugged into a connector which is on another motherboard, and then they are subjected to current stressing through that connector there with the various contacts, which the through holes for which are shown on the left of the board there. And then we set the board up on a shock table and we drop it, and then we collect the viable data, collect the data wherever we get a failure. The number of temperature cycle is actually not temperature, it should be shock, number of shock drops, and then we plot the probability and try to see if there is a variation in the characteristic life as you migrate the bismuth towards one end of the solder joint. So that's the mechanical shock reliability experimental setup. Next one. And that's the sign-up procedure, which I believe Haley will cover.
Yeah, thank you, Ren. Next slide. So for those who are familiar with NEMI, we have a project development process. In fact, for this project, it's a continuous project. We have multiple phases as introduced. So at the beginning of the project definition, we already defined the 3 phases. But for the second phase, we detailed the plan after we finish the phase 1, and we understand where we need to explore further, and we adjust the test vehicle design, the experimental design, etc. So we have 2 documents. I will introduce next slide, the SOW and the project statement. So we have those 2 documents reviewed by the technical committee. It's approved. So the project is open for launch to sign up. Any company who are interested in this project, they can decide to join. According to the NEMI project management policy, we only the NEMI members can join the project because it the work and the resource and the data sharing, this type of things need to be done within a close group. And the NEMI membership, the bylaws provide the legal framework so that people or companies, they can collaborate under this legal terms. So the next slide, the companies who want to join the project, if you are already an NEMI member, you can just download the SOW and review it and sign the project statement for the second phase. After your signature is filling in the form. So in fact, for each company, even though maybe there are multiple people who would like to participate in the project or get access to the project, only one form is required for joining the project, because the participation is signed on behalf of the company. Okay. Once you finish, you send back the copy to me, and we will have the NEMI CTO, Grace O'Malley, to review and give the acceptance approval for the participation. So if you are not an NEMI member, and if you are interested in the project or maybe some others, you can contact us, myself, or any NEMI staff in your region to discuss. Okay, for this project sign-up is due by the end of this month. Okay, I think that's all we have. We will open the floor for questions. You can unmute yourself or input your comments or question in the chat or Q&A. That's fine as well. I don't see any questions in the chat.
Hello.
Yeah, go ahead.
Just now you mentioned that finishing doesn't play a role for BTC, right? Does it play any role in the SEC 305 study that you did?
Well, so what's the question? I didn't follow.
The surface finishing.
Surface finish.
Yeah.
Oh, surface
Doesn't
finish.
play a role in BTC. Does it play any role in the SEC 305 study that you did?
Yeah, so we showed in SAC 305, it plays no role, correct? No, sorry, no. In SAC 305, the surface finish plays a role. And, sorry, so what happens is it plays a minor role because even though the CU6 SN5 forms like crazy in the case of OSP, the CU6 SN5 resistance is not too different from tin. It's a little higher, not too different. So, yeah, so if you look at the microstructure, you see a big difference, right? But electrically, you don't see much difference. That's very interesting. So if you were only to look at the microstructure, you would say, oh, gee, look at this. OSP is giving us so much intermetallic formation, but the resistance difference between OSP and ENIC is not much. So that's my answer. Any other question?
Okay, any other questions from audience? People ask if we get this. Yes, the presentation material will be shared. Okay, probably sometime next week, my colleague will distribute the presentation slides and the recording, the link to the recording. Okay. Any other comments, questions, or suggestions?
Yeah, this is Jay Krishna from Omicron. May I know when are we expecting this to just be out from reliability point of view, both shop and I think some test is ongoing.
Yeah, I think you can go look at the schedule. Can you put up the schedule again?
Okay.
Is that what you're asking about, the schedule?
Yeah.
I think for end of the year, the shock reliability is a Q4, maybe was in the fall, starting fall.
Okay. Thank you. Thank you.
Okay, any additional questions, comments before we close today's session? Okay, if not, I would like to thank PJ and Rel for the presentation, and also thank you all for your interest and attend this webinar. And we hope to collaborate in the future. If you come up with any question or comments, you also can contact us later on. Okay, thank you.